Hi, everyone. Welcome to Performance Tuning Games for Hybrid Architectures. I'm Pete Brubaker. Prepared this slide deck with Sheng Guo from China, but he was unable to travel to GDC this year, so I will be presenting. Our agenda for today, we're going to talk about Intel hybrid processors, the core topology, their instruction set architectures, performance characteristics, how to detect this hybrid topology, how thread scheduling works with hybrid processors, and some other changes with respect to model-specific registers, last branch records, and CPUID. And then we're going to go through some best practices for games on hybrid processors and some resources for you to take away after this presentation. Right, so let's get into the core topology. So Intel 12th Gen core processors, formerly known as Alder Lake, with hybrid technology. We launched in 2021 with multiple hybrid SKUs. We had a few high-level goals: balance performance and power efficiency in a small footprint, enable design flexibility for mobile form factors such as foldables or ultralights, and offer multiple SKU configurations to support a range of markets, including desktop. The two cores that are in this processor are Golden Cove and Gracemont. Golden Cove concentrates on single threaded and limited threading scenarios. It's performance focused, and we call these P cores. The Gracemont core concentrates on throughput and power limited scenarios, so they're efficient cores. They're efficiently focused E cores, and the area of 4 E cores equals about 1 P core. So we could fit four times the amount of Gracemont cores on the die that we can Golden Cove. This also contains Intel Thread Director, which is a hardware accelerated scheduling system, and it provides operating support with Microsoft Windows 11, and we'll get into that here in a minute. Here's an example of three of the SKUs. We have desktop, mobile, and ultra mobile. You can see the desktop has 8 P cores and 8 E cores. The mobile has 6 P cores and 8 E cores, and the ultra mobile has 2 P cores and 8 E cores. Each SKU uses the same core architectures. The difference here is the number of performance and efficiency cores contained in each package. Developers should be aware of the asymmetric topologies related with Alder Lake and design your thread scheduling algorithms to be adaptable as possible to achieve the greatest total available market for your product. So let's talk about the performance and E-cores, performance and efficient cores and their differences. Performance cores offer higher frequencies. They're designed for higher frequencies, but they're less efficient. Additionally, they also offer hyperthreading, which splits a single physical core into 2 logical cores. P-cores have a different efficiency class than E-cores. CPUID has a different flag for each P-core and E-core to allow you to tell the difference. The cache topology of a performance core is 80 kilobytes of L1 that's split evenly with L1D and L1I, a dedicated 1.25 megabyte L2 cache, and a shared 3 megabyte LLC or L3 last level cache. And it's shared with efficient cores. So it's 3 megabytes per P core. Efficient cores are they're designed for power efficiency. They're designed to use less power at lower frequencies for less critical work. The instruction set architecture is symmetric with the P cores. So AVX512 is disabled on P cores and E cores, and SSE and AVX2 are available on both the Golden Cove and Gracemont cores. The cache topology of the E cores is a little bit different. It's got a 96 kilobyte L1 cache that's divided evenly between instruction and data. There's a 2 megabyte L2 cache that's shared in banks of 4 E cores. 512 kilobytes per E core roughly. And then there's 3 megabytes of L3 cache per 4 efficiency cores. And that L3 cache is also shared with performance cores. So let's talk about core ICEs a little bit. To simplify the programming model and provide flexibility we made a few design decisions. All core types have the same basic instruction set, SSE, AVX, AVX2. TSX is disabled on the package, as well as AVX 512. And you should note that if you try to use one of these instructions, you'll get an illegal instruction exception. AVX VNNI is a VEX encoded variant of AVX 512 VNNI that's limited to 256-bit registers. This is a new instruction set for this platform. It doesn't support any of the additional features of EVEX encoding, so no mask registers or the additional vector registers that are available in AVX 512. We've also introduced carryless multiplication with this platform, PCL mul QDQ. It's useful in the multiplication of polynomials and could potentially have a use in games with compression and CRC hashing. Another set of new instructions on Alder Lake is tpause, umonitor, and umwait. For short waits on the order of tens to hundreds of microseconds, we typically resort to busy loops to avoid calling into the kernel. And on Alder Lake and newer, these new instructions, umonitor, uwait, and tpause, we can use those to replace those busy loops. These are unprivileged instructions and avoid calling into the kernel. They're effectively the same as monitor and wait instructions in SSC3 in the sense that they will cause the processor to do the same things as umonitor, uwait, and tpause. umonitor takes an address and a size, informing the CPU that the thread that called those instructions is interested in any writes to that range of memory. umwait tells the CPU to halt the instruction until a write in that memory range occurs or a timeout is reached. This allows the CPU to switch to an SMT sibling or enter a lower power state, CO1, that can be exited quickly. Keep waits short on the order of 10 to 100 microseconds. This will avoid the CPU switching to a lower power state that may take longer to exit. The tpause instruction is almost identical to umonitor and umwait, except the CPU will not monitor for any writes. It'll just wait for a timeout. And a single tpause instruction can replace a loop with an pause, waiting for a counter to expire. So with this platform, we need to change some of our assumptions. There can be a significant delta in performance between cores. Even identical cores may run at different frequencies. There may be 1, 2, or more faster cores on the package. The fastest core may move around the package due to thermals and efficiency. Hyperthreading may only be available on some cores in the package, so using logical core count may not equal 2x physical core count. The core topology layout may not be simple. Performance ordering or relationship between logical cores may change. The ISA may be identical, but specific performance of an instruction may vary, and we'll get into that in a bit. Running efficiently or slower may be faster overall. So switching things to E-cores, while it may take longer to run, it may be more power efficient. And power may be shared on the package between the GPU, the CPU, and other silicon, and may affect the frequency of the package. So let's talk about some of those performance characteristics. So integer and floating point instructions, performance is about equal between P-cores and E-cores, with E-cores operating at about 70% of a P-core, or 0.7x. SSE and floating point operations are a bit slower on E-cores. 4-wide floating point operates at about 0.4x the performance of a P-core. And on AVX and AVX2, E-cores operate on 8-wide floating point data at about 0.4x the performance of a P-core. So many jobs that typically get scheduled in a game job system make moderate to heavy use of SIMD. So this means we need to be selective about which jobs run on which core. Hardware-guided scheduling and Thread Director help here on Windows 11. We also need a solution for Windows 10 and earlier. And given the cache differences, the shared L2 on E-cores Some workloads might even perform a bit better if they're allocated to cores that share L2. So what if we just throw all the low priority threads on E-cores? So this is an example from a Tech Power Up article where they were doing some performance measurement. On Windows 10 or below, normal priority threads are scheduled on E-cores by default. And here we can see Unreal creates two thread pools sized by logical core count -2. One above normal priority and one pool at normal priority. And these 44 threads are fighting over 8 P cores and 8 E cores. And we see here that Windows 10 performance suffers. On Windows 10, we're oversubscribing the E cores, and performance will be much less than ideal. It's also possible that SIMD heavy work is being scheduled to E cores on Windows 10. So Intel Thread Director solves this issue for us on Windows 11 and beyond. We can see that as that's the best performing solution here. Thread Director will also favor scheduling threads with AVX and AVX2 instructions on P cores, which can cause issues even on Windows 11. The OS has to choose which thread to schedule to P cores, and when the system is oversubscribed, occasionally tasks on the critical path can get scheduled to E cores, especially if all the P cores are busy executing SIMD heavy workloads. Thread count impacts performance by not only parallel width, but also threading overhead, power consumption, cache contention, etc. On hybrid, oversubscribing E cores may increase overhead and reduce P core performance for critical threads. Just optimizing thread count may improve your performance. So we need to be careful what work we put on E cores, and we also need to be careful not to oversubscribe them. We also can't assume something that works well on desktop, or 8 P cores plus 8 E cores, will work on mobile, which is 6 plus 8, or ultra mobile, which is 2 plus 8. Intel Thread Director on Windows 11 helps mitigate this issue, as we see that Windows 11 with E cores enabled beats Windows 10 with E cores disabled. So what is this Intel Thread Director? Intel Thread Director, or Hardware Guided Scheduling Plus, is a scheduling that helps the OS schedule the right thread on the right core. It sets priority between threads when the number of threads exceeds the number of cores. So this is one reason, again, why you want to limit your thread pool size to the number of physical cores. The goal is to achieve the best power and energy saving without sacrificing performance. The threads are scheduled based on thread class type, and that includes the type of instructions that they're executing. It could be integer, VNNI, AVX2, floating point 32, etc. Hardware provides feedback about the thread class through model-specific registers, and it's Windows 11 only. So P-core versus E-core power and performance depends on power and thermal efficiency, as well as power and thermal management. Hardware dynamically generates core capabilities based on power and thermal limits, and it provides this information back to the scheduler. The scheduler then determines the best core for the specific ISA and the specific thread. And Thread Director, again, will also favor scheduling threads with AVX, AVX2, and VNNI instructions on P cores. So the OS scheduler will move threads based on the information you give it, priority, quality of service, performance, and efficiency metrics provided by the hardware. P cores scheduled first, and then spillover multi-threaded work gets scheduled to E cores. And SMT siblings are used last to avoid any contention impacting performance on L2. Busy waits, spin waits, TPAWS, wait on P cores, those threads are automatically switched to E cores. Busy thread, except for busy waiting on E core, will be switched to an idle P core. But this changes with the power plan settings in Windows. So when using a balanced power plan, Windows 11 will schedule the threads spawned from the InFocus window process to the P cores. Background window threads then get scheduled to E cores. This will affect background processes as they cannot be in focus. This is by design by Microsoft and regardless of thread priority. So what do we do about Windows 10 and earlier? Intel Thread Director and hardware guided scheduling sound cool, but we can't use them on Windows 10. Let's talk first about hybrid topology detection, because we're going to need to do this first in order to detect a hybrid processor. There's a few ways that you can go around it about it. The CPUID intrinsic is what you'll use to determine the core types, processor type and core type. It requires pin in a thread to read from each logical processor. It may return invalid data in Windows compatibility mode. It's cross-platform and support for x86, x64, Windows, and Linux. Useful for determining the supported ISAs and frequency, and you can read hybrid and core type from the hybrid leaf. There's also get logical process information. This will allow you to enumerate logical processors and caches without pinning. Uses a 64-bit affinity mask as identifiers for cores and caches. Masks are compatible with set thread affinity masks, so you can go right into affinitizing your threads. But this is kind of the old way of going about it. Windows 10 and Windows 11 introduced a new API called Get System CPU Set Information. This works with more than 64 logical cores by default. It shows which cores share an LLC, so you can identify cores that share L2 and prioritize work that benefits from sharing L2 to these cores. Returns an efficiency class and parking flags. It's only available on Windows 10 and newer. You can use it in combination with Get Logical Processor Information and Get Logical Processor Information EX. It uses integer-based identifiers instead of affinity masks. And finally, there's a Get Logical Processor Information EX. The processor relationship structure that it returns shows the efficiency class for each processor. It uses group masks with a group ID and a 64-bit affinity mask. The masks are compatible with set thread affinity mask, and it works with more than 64 logical processors by default. We would recommend that you use this instead of Get Logical Processor Information, as that API is somewhat out of date. Right, so now that we know how to detect these cores, how do we control the scheduling? Well, there's a couple of different ways. There's a weak partitioning and there's strong partitioning. We're going to go through both, but we really recommend that you use weak partitioning so the hardware guided scheduler can override your choices if it's better. Let's go over the quality of service APIs. So there's set thread ideal processor. Using this is more likely to be scheduled on the ideal processor, though it is not guaranteed. It's useful for targeting Turbo Boost 3 cores. There's set thread priority, which is useful for creating critical path threads with above normal priority. And you can also set background worker threads with this function. There's also set thread information, which allows you to disable power throttling for maximum performance, or you can enable power throttling for maximum power efficiency. And you can set the memory priority for more efficient cache utilization. Using these APIs will allow the OS to override your choices. Like, let's say you have a thread running on a P core that switches to an idle loop or a busy loop or a T-pause or wait. This will allow the OS to switch that thread to an E core. If you use strong APIs, that won't happen. The OS won't be able to do that. The static partitioning APIs we have are set thread affinity mask and set thread selected CPU sets. So in addition to set thread affinity mask, we have set thread selected CPU sets. This is my preferred API. It's very similar to set thread affinity mask, but it doesn't use bit masks. It supports more than 64 logical processors without group masks. And the OS power management can override CPU sets, which is a good thing. Right, so let's talk about some other changes with the platform. First up, we've got CPUID is slightly different. There's 2 new flags that have been added. The hybrid flag, this is readable by calling CPUID with 07H in the EAX register and reading the 15th bit of the EDX register. This will let you know that the CPU is a hybrid CPU. And then next, you'll need to detect the core type flag. This is readable by calling CPUID on each logical processor with a value of 1AH in the EAX register, and the core type will be returned in bits 24 to 31 of the EAX register. This will let you know if the core is core or atom. It's important to note that CPUID will return different values for the core type flag for both P and E cores. So if you're using this to generate a globally unique ID for machines or gamers, take care that the core that you're using to create this is deterministic. One other thing that's different on this hardware is we've introduced architectural last branch records. These enable the recording of software path history by logging the taken branches and other control flow registers within the processor. Each LBR record or entry is comprised of 3 MSRs. There's the from IP MSR, the to IP MSR, and the info MSR. From IP holds the source IP of the operation, to IP holds the destination IP of the operation, and info holds metadata for the operation, including mispredicts, TSX, lap cycle, time information, etc. You can check for support of this using the EA CPUID flags below. If it's set to 1, the processor supports architectural LBRs and does not support legacy LBRs. So LBRs are typically used in games in anti-cheat, DRM, and anti-tamper code. LBRs, while they have been model specific in the past, they haven't changed in a long time. So Intel has introduced architectural LBRs for Alder Lake and beyond so that these can be updated. This could present an issue for legacy code relying on legacy LBRs, and indeed it has, but we believe we've solved most of those. And this is fully documented in Chapter 7 of the March 2020 and newer Intel Architecture Instruction Set Extensions Programming Reference. So best practices, profile your workload. Use Query Performance Counter for micro benchmarking, and use Intel vTune Profiler for in-depth CPU performance analysis. Don't oversubscribe your thread pool. Don't use hyperthreaded cores if your workload can't benefit from hyperthreading. Avoid unnecessary context switches and cache flushes. Use quality of service APIs for OS and Intel Thread Director optimization. Quality of service APIs can be used in combination with static partitioning APIs based on application architecture. Avoid static partitioning, allow cores to steal work from other cores. Work stealing allows idle threads to take tasks from cores that may be overloaded and will increase throughput. Avoid pinning threads to a single processor. Avoid scheduling lower priority tasks on the same cores as your critical path. Understand how your middleware uses threads. And job systems need to dynamically balance based on core characteristics. So what are the best practices for scheduling game subsystems? Right, so for critical path, we suggest all of those threads be on P cores or high priority. Main and rendering and audio threads, those are important. We want to submit draw calls to the GPU as fast as possible. We can disable power throttling to get maximum performance on these threads. And you can use set thread priority boost for opportunistic priority increases. And audio, because we want to make sure that audio stays in sync with the rendering. Time critical jobs or jobs with heavy use of floating point, we want those to be on P cores, things like collision detection, physics, animation, etc. And scene visibility and CPU occlusion culling, we want that to also be scheduled on P cores. We want to maximize our triangle throughput by using performance cores. And we also use SIMD in those workloads to increase data parallelism, so they're prime candidate for P cores. Some of the systems we think are particularly well suited to E cores include input-output, compression and decompression, integer workloads, texture streaming, shader compilation, input, UI, networking, VoIP, and background NPC or game AI. We think these are all good systems for E cores. Lastly, we have a great sample that was prepared by my colleague Marissa Dubois. This is Hybrid Detect. It's basically all these APIs that we've talked about and examples of how to use them. You can also use this as like a CPUID browser. It shows package information on Windows 32 and DX12, Intel is hybrid, Component counters, it shows if this processor has Turbo Boost Max 2 or 3. You can read all of the bit masks, the system and process masks, custom masks, logical processor masks, logical cache masks, and it's really useful for debugging and looking at browsing the CPUID features. You can also get architecture details, logical processors, base frequency, current frequency, max frequency. It's a really useful tool, and the code's really great, and it'll help you utilize these APIs that we've talked about in this presentation. To wrap up, we have a couple of do's and don'ts. Do's, plan ahead for future hybrid architectures. There's more of this in the pipeline, and more processors coming in the future will feature hybrid cores. Enumerate hybrid cores with heterogeneous topology. We need to know if this package supports hybrid processors, and we need to know which cores those are. Set appropriate thread priority and quality of service information for your game jobs. Identify and set the optimal thread count. Allocate just enough threads for your workload. Use a work stealing thread scheduler if possible. And understand the performance trade-offs between performance and efficiency cores, and take advantage of the performance deltas by putting the right work on each core. And don't oversubscribe your cores beyond your needs, and don't pin threads to certain cores using affinity. I'd also like to give a shout out to a couple of contributors of content presented here today, Sheng Guo and Marissa Dubois. They both helped with some of these slides in here, and I'd like to thank them very much. And here are some links and resources for you to take this information further. We've got the developer guide, which contains more in-depth information about Alder Lake than we've presented here. Obviously, the vTune profiler, this is key. Sample code for Intel Hybrid Detect, and a link to the programming reference, as well as links to all of the Windows API functions referenced in the talk. Thank you very much.